This is Project 5 Video 1, the pencil and paper part. Got a line of charge along the y-axis from minus 25 millimeters to 25 millimeters. Given this charge density, write a function that gives you the x component of the electric field, and then another function that uses that to graph it. Alright, so I can draw the picture here. I'll get coordinate system. Y comma y prime, x comma x prime. Here's the charge distribution from, call it minus a to a, where a is equal to 0.025 meters. And we're looking for the x component of the electric field at points on the x-axis. So I'll pick a point over here. It'll be a distance r away from, I'll call this point P, which is at x comma 0. And here's the contribution to the total electric field, this magnitude times that direction, due to this little bit of charge dq, which is lambda dy prime in this little line segment that's got a length dy prime. And lambda is given as, let's see, 1 microcoulomb per meter squared times y. 1 got times 10 to the minus 6 coulombs per meter times the absolute value of y. Call it y prime. Now here's the thing, for any little bit of charge, a distance y prime up, oh, and by the way I should say how far up it is. There's going to be one that's y prime down, that because the linear charge density just depends on how far you are away from the origin, it'll be the same exact amount of charge if it's at the same distance below the origin. And it'll create an electric field that's up and to the right. First we notice and it's going to be of the same magnitude. And at the same angle above the horizontal axis that the other one from the bit of charge above is below the horizontal axis. So first off, the y components will cancel out. Well, it doesn't really matter that much because I just asked for the x component, but there is no y component. But the other point is, these will be of the same magnitude, same angle. They're going to make the same contribution to the x component. So I can argue, and I have to write down my argument, from symmetry, and it's because the charge distribution is symmetric with respect to the origin. The phi at x comma 0 is equal to 2 times the phi due to charge on 0 to 25 millimeters. So I don't have to do the whole integral. Also above that axis, where y absolute value, or the absolute value of y, is just equal to y. So I'm going to take advantage of that a little bit later on. Say right now 2 times, and by the way, that was e sub x I'm solving for, so better fix that up. Alright, so it's all about the x component of the electric field. So dE is equal to k dq over r squared. Let's see what r is. R is equal to the square root of x squared, where point P is, plus y prime squared. And the lambda, I'm going to call that, I'll define this as b, at least for the moment. So lambda is equal to b times y prime on for let's just say where which is the only place I need to investigate because of that symmetry argument. So let's see, this is k times lambda. That looks like an x. Oh, I think I wanted to fix up, yeah, I guess I'll have to leave it like that. K lambda dy prime, all divided by square root of x squared plus y prime squared. Squared, which is k, so lowercase k, b y prime dy prime over square root of x squared plus y prime squared squared. And then dE is down at this angle theta, which appears inside this positional triangle. I think I'll work on dE right here where I can see what's going on. So dE dEx, and this will be the magnitude of dEy. dEx is equal to dE cosine of theta. But from this triangle over here, cosine of theta is equal to it'll be, this distance is x, so it'll be x over r. So DEX is equal to DE times x over r. Alright. DEX is DE times x over r, which is equal to KBY prime dy prime over the square root of x squared plus y prime squared all squared times x over square root of x squared plus y prime squared. So DEX is equal to x squared. I think I'll write that as y prime squared plus x squared all to the 3/2. I'll integrate that on both sides. And I got EX. Oh, by the way, what I'll do is put a factor of 2 in there. And just go from 0 up to y. No, to a. Again, the factor of 2 comes from the symmetry argument. And limits just from 0 to a, rather, from minus a to a. Alright. Call this 2 k bx from the, times the integral from 0 to a of y prime dy prime all over y prime squared plus x squared all to the 3/2. I just have to find that integral on the formula sheet. And there's one that's x dx, integral of x dx over x squared plus a squared all to the 3/2. So our x in our actual expression is going to be playing the role of a, and our y prime is going to be playing the role of x. So from formula sheet, we get that this is equal to 2kb times x times a minus 1 over the square root of y prime squared plus x squared. I don't like that square in there. Let's see if I can make that a little bit more clear. Actually, the prime is a little off too. So I'll make it y prime squared plus x squared. Evaluated from 0 to a. Y prime goes from 0 to a. So this is 2, I think I got the equal sign in the wrong spot. Just need some parentheses or something, so that's multiplication, not subtraction. So 2kbx times minus 1 over square root of a squared minus x squared minus 1 over the square root of 0 squared plus x squared. It was plus in both cases. So that'll be 2kbx times, I'll take the minus and minus, makes this term plus, and that's going to be 1 over x. And I got to be careful. It could be the square root of that gives me plus or minus x. I have to think about that. And then minus 1 over this. This will be a positive contribution, or e sub x. If x is positive, so 2 to the right of this, positive charge distribution, with this being a positive x, this 1 over is going to be bigger than this 1 over, so this will be positive, and so indeed this x has to be a positive value. And I think I'll call that, I'm going to go ex equal 2kb, and x times 1 over x is a 1. And then I've got x over all this. I'm going to divide top and bottom by x inside the square root. It becomes 1 over. So I have minus 1 over, no, inside the square root it becomes an x squared. So I'm dividing each term under the radical by x squared. I'll get a 1 when I divide it into that term, plus a squared over x squared, which I'll call a over x squared. Alright. So I think that's all we need for the first function, and then the second function is used to graph that. So outline, the code outline. I got 2 functions. Just call that one ex function go e underscore x equals ex of x. And I would need to initialize some variables, so I'll set k equal to 8.99 times 10 to the 9th. Newton meter squared per coulomb squared. B equals 1 times 10 to the minus 6 coulombs per meter squared, if I recall correctly. Let's take a look up here and make sure I got that right. B is 1.6 times 10 to 1 times 10 to the minus 6 coulombs. I've got it written down as coulombs per meter. Coulombs per meter squared, so I had that wrong. Looks good now. And F prime looks too much like a dot. Alright. So that is B. A was 0.025 meters. I got it right here. A equals so that's K, B, and A, and then X is passed as an argument, and so I'll just say eval. Oh, I think I'll write it out because I want to set E underscore X. My function name is EX, and E underscore X is my return variable name. So I'll go 2 times K times B times 1 minus 1 divided by square root of 1 plus a slash X squared. Alright. And then I go function. This one doesn't have to return anything. Plot. I think I'll call it graph, just in case there is such a thing. This plot. So graph EX, and I don't think that needs any argument. I'll go. You're supposed to graph it from what to what. I gotta look at that. I think I'll go X lin space of. Alright, let's see. Just what it was that I had to grab. Minus 0.025 to 0.025. Minus 0.025 to 0.025. Try 100 of them. If that doesn't look smooth, I'll jack that up. And then plot. Oh no. I'll go E. I think I'll go ahead and call it E underscore X here as well. It's okay to duplicate that. Equals E X of X. I think I'm going to need, I'll need some dots in here when I actually go to use it. But I think this should evaluate. This will use this function to find values of EX at every X value in here. The 100 X values from here to here. I I think I'll call it 101 in case I want to look at those numbers. It comes out a little bit better because it's the fact that I'm using the starting point. They'll divide up more into 100. If I have 100 values, then I've got 100 intervals. 101 values, I'll have 100 intervals, and each interval will just be 0.0025. So I think I like that better. And then plot x, comma, e underscore x. So when I do this, I get 101 values in e underscore x, 101 values of e sub x at the 101 different values of x, and then that graphs it. And I think that does it for the pencil on paper part. So I'm going to call it a wrap.